to find the eigenvalues of this matrix. So the first step, of course, this must be a square matrix. The first step is to write down a new matrix, which is a scalar matrix, lambda times identity, minus our matrix, okay? So what is lambda times identity? If my matrix is 3 minus 1, 4 minus 2, what is lambda identity? Is lambda times the identity of order 2 So, based on the sum of matrices, lambda identity minus A is just lambda minus 3, 1, minus 4, lambda plus 2, okay? And we need to
Excuse me, Professor, could you please share your screen because we can't see what you're writing? Thank you.
Thanks. No, but it looks like I'm sharing my screen.
I can see your screen.
I guess it's just my problem. I'll try coming back in. Sorry.
No problem, but can you see my screen? What about the other students? Now, of course, I have to go back to the slides, but can you see the slides?
Yes.
Yes.
Okay, thanks. So lambda identity minus A is this one, basically. We have to build this matrix. Okay? And when we want to obtain the eigenvalues, we have to solve the equation determinant of lambda identity minus A equal to 0, which is an algebraic equation of order n. In this case, it is a quadratic equation, because the dimension of the matrix is 2. In general, it is an equation of order n, a polynomial of nth degree equal to 0, okay? This is called characteristic equation. As usual, if we have two real and distinct solutions, we call these solutions lambda 1 and lambda 2, okay? And when we have the two eigenvalues, we can compute the eigenvectors associated to each eigenvalue by just solving lambda identity minus A times x equal to 0. Okay? This is a system, in our case, of two equations in two unknowns. Basically, if we here replace lambda 1, the first eigenvalue, and we solve the system, we find the eigenvectors associated to lambda 1. If we do the same with lambda 2 identity minus A, where lambda 2 is the second eigenvalue, okay? This is what we do. Why is this the equation? Why, given the eigenvalue, for instance, given this one, why is this the equation, which is a system of equations, by which we can find the eigenvectors? Because you can write this one as lambda 1 identity x is equal to ax, okay? But lambda 1 identity times x is x, okay? So lambda 1 times x is equal to A times x. And this is the definition, remember the definition of eigenvalues and eigenvectors. If there exists a number, lambda 1, given a matrix A, if there exists a number lambda 1 and a vector x such that multiplying the number, the scalar, times x is the same as multiplying the matrix, the given matrix, times x, lambda 1 is called an eigenvalue of the matrix, and this x is called an eigenvector associated to the given eigenvalue, okay? So this is basically the way we then solve. So the first step is finding the eigenvalues. And the reason why we solve this equation is that we are not interested here in trivial solutions. This system always has the solution x equal to 0. Only in the case where the determinant of this matrix is equal to 0, we have additional solutions and not just the 0 solution, okay? So we have to put determinant equal to 0 in order to find the eigenvalues. And next, for each eigenvalue, we find the eigenvectors, okay? If the determinant is not equal to 0, then the system, this one, has only the trivial 0 solution. It is an homogeneous system with coefficient matrix with a non-zero determinant, has only the trivial solution, where the trivial solution is 0. But we are interested in solutions that are other than 0. Other than the 0 vectors. So first of all, find the eigenvalues. So this, you usually find 2 if the matrix is a 2 by 2 matrix, or 3 if the and the left-hand side is called characteristic polynomial. Since the matrix is a 2 by 2 matrix, it is a second degree equation. It has 2 solutions, -1 and 2. -1 and 2, for each one, we want to find eigenvectors. So consider -1 first. -1 identity is this one. Minus A, compute the sum of these 2 matrices, you obtain the new matrix, lambda 1 identity minus A is -4, 1, -4, 1. You see that clearly the determinant here will be 0. It must be 0, okay? It must be 0 because we selected the values of lambda such that the determinant is 0. And the determinant is 0 because the 2 lines here are the same line, so they are proportional to each other, okay? When 2 lines are proportional to one another, the determinant of the matrix is 0. This is a property of determinants, okay? And I mean, you don't need to know this property because if you write down the system, or here there is x1, x2 missing, of course, but if you write down the system, you get 2 equations that are equal to one another. From this, we get x2 equal to 4x1, and means that our vector is written in this way. Any vector with this property. The second component is 4 times the first component. Okay? So we take 1 among them, we multiply by a scalar alpha, and we get, in any case, we get a vector in which the second component, which is 4 alpha, is 4 times the first component, which is alpha. Where alpha is any real number, we exclude 0 just because we are not interested in the vector 0, 0, okay? Okay, so these are the eigenvectors associated to the first one, and these are the eigenvectors associated to the second one. To the second one, I do the same. Okay, I now replace lambda 2 here. Lambda 2 was 2. If you do this, here you have the matrix, scalar matrix with 2 in the main diagonal minus this one. So the new matrix lambda 2 identity minus A is just this one. Again, you see that the second line is 4 times the first line. So basically the two equations give us the same information. So in fact they are a unique equation, which leaves some indeterminacy in the solution, right? We cannot find a unique pair x1, x2 that solves the system. We have infinitely many, and they can be written in this way. Okay? If you solve this, you get x2 is equal to x1. So 1 times any scalar beta. And the second step, the next step is, which is useful also for the graphical analysis, is of course to be able to represent the two eigenvectors associated to each eigenvalue as straight lines in the plane. The second one, this is the eigenvector associated to the second eigenvalue. x2 is equal to x1, in the plane x1, x2 is just the bisector, okay? And the first one was x2 equal to 4x1, is this one, is the straight line of equation x2 is equal to 4x1. Of course, the infinitely many eigenvectors associated to each eigenvalue are not random points in the plane, okay? You know, a point in the plane represents a vector. They're not randomly spread in the plane, okay? So they are ordered along some straight line, okay? So they are called linear subspaces of the plane, okay? A straight line is a linear subspace of the plane, a plane is a linear subspace of the three-dimensional space, and so on and so forth, okay? So there are some properties that are related to the theory, so-called theory of vector spaces, but we are not interested in this now. We are interested in using eigenvalues and eigenvectors to find a solution to linear systems of two autonomous differential equations, okay? Or systems of two linear autonomous differential equations. There are two main remarks that are basically just let me check one thing in a moment. Of course, I have to keep track of what's happening in the department meeting. Okay, so there are two main remarks about eigenvalues and eigenvectors. There is one case in which it is extremely easy to find the eigenvalues of a matrix. And this is the case in which we have a triangular matrix. Like this, for instance. This is called lower triangular matrix. Okay, if the matrix is triangular, the eigenvalues are already there, displayed in the main diagonal, okay? They are 1 and minus 2. And another thing is that if you have a 2 by 2 square matrix, you don't really need to build lambda identity minus A and then compute the determinant, because it can be shown in general that the characteristic equation can be written directly in this form. Lambda squared, it is a second degree polynomial. So lambda squared minus trace of the matrix. The trace of the matrix is the sum of the elements in the main diagonal. Okay, so the trace of this matrix is, for instance, 3 minus 2, 1. And the determinant is minus 6 plus 4, so minus 2. So we can write directly the characteristic equation, lambda squared minus trace times lambda plus determinant. Okay? You can check with the previous example that the characteristic equation that you obtain, which is this one, determinant of lambda identity minus A equal to 0, which becomes this one. Okay? is exactly lambda squared minus trace times lambda plus determinant, okay? So you can write the equation directly. So you can write the equation directly, which is very convenient. It is very convenient, and it can be proven very easily. Okay, if you build a lambda identity minus A in general, you write down the characteristic equation by computing the determinant of lambda identity minus A, and you get this. This is the trace, and this is the determinant, okay? So it's very easy. So I suggest to use this formula because it's easier. Saves time. Okay, now I'm going to show you how we can use this eigenvalue and eigenvectors for the solution of linear systems of differential equations. Okay, so the next step is systems of linear, autonomous, first-order differential equations. Linear, autonomous means that the coefficients, both the coefficients of the matrix, coefficients that multiply the variables, and the constant terms do not depend on time directly. So autonomous. First order, because only the first derivatives appear in the equation, first derivatives and the value of the functions of time. Okay? The structure is like this. Remember the structure of the equation. X dot plus AX, because for some reasons in the case of the equation it's useful to move the term in X on the left side, but it's only for convenience, is equal to B, or if you like, X dot is equal to minus AX plus B. Okay? And for a system we do this. X dot, the vector of the derivatives of two functions of time, two functions, is equal to matrix A times X, the vector of the two functions, plus B, vector of the constant terms. And with matrix notation, it is like this. I illustrate this for convenience only in the case of two variables, but many results extend to the case of three variables, four variables, and so on and so forth, okay? Of course, what becomes more difficult in that case would be to compute the eigenvalues of a four-dimensional matrix and the eigenvectors, but what I write here in terms of results, of theorems, of formulas, is the same for any dimension of the matrix. So what is the meaning of X dot equal to AX plus B? Each of the time derivatives, the time derivative of each of the two functions of time, there are two unknown functions of time, x1 and x2. Their derivatives, both of them, in principle, depend on the levels of both variables. For instance, at a given point in time, the time derivative of variable x1 depends on both the level of x1 and the level of x2. Okay? At the same time, the time derivative, that is, let's say, the trend, the direction of the evolution of the second variable depends both on the state, on the level of the first variable, and on the level of the second variable. So we have two unknown functions of time. And with matrix notation, we have this. Just because the matrix product is here, you get A11x1 plus A12x2, okay? Plus B1. Or the second equation will be A21x1 plus A22x2 plus B2. So this is the matrix notation. Now, let me show you how we can arrive very quickly at the solution formula for this system. Okay. The way we arrive at the solution formula is very intuitive, and it's based on that principle of guessing the structure of the solution. We know that when we have an equation, x dot, let me start first from the basic case, x dot equal to ax. Okay, plus b, now it is equal to 0, okay? Next, we will add b. So we want to solve x dot equal to vector equal to ax. So basically here, we don't have b1, b2. We have only this one, a11x1 plus a12x2. b1 is 0. And the same for b2. b2 is 0. This is called homogeneous system of equations, okay? Because the constant terms are 0. We want to solve this one, but we know something already about its one-dimensional counterpart, which is x dot is equal to ax, okay? What is the general solution to this simple equation? Remember the constant growth model, basically, okay? xt is equal to c, an arbitrary constant, times exponential of at. So what we do now is to guess that also in the, for instance, in the two-dimensional case, the structure of the solution will be similar, okay? So we guess a solution of this type. x1t, we have two variables, okay? x1t will be some constant c1 times the exponential of some constant that we call lambda times t. Okay? And x2 of t is equal to c2 times the exponential of the same lambda times t. We wonder whether there exists a solution to our equation, which is a system of equations, having this structure. For some C1, C2, and lambda, okay? We wonder whether we can find a lambda to put here at the exponent and two constants, C1 and C2, such that this one is the solution to this system of equations. The interesting thing is that we can write this in vector form, okay? So we look for the existence of a solution of this type, x1, x2 of t equal to c1, c2 times, there is a common number that multiplies both here, exponential of lambda t. Of course, it's a function, it depends on t, but it is a scalar, it is not a vector. So times a constant, okay? Times exponential of lambda t. Okay, so we are looking for a solution of this type. X of t is equal to some vector c times exponential of lambda t. Okay? Okay, so if there exists a solution of this type, if our conjecture is correct, remember that these two functions must satisfy our differential equations, okay? Then, what is the derivative of x1 with respect to t? It is equal to lambda c1 exponential of lambda t, okay? And what is the derivative of our variable x2 with respect to time? It is lambda c2 exponential of lambda t. So basically, if this is true, the vector of the derivatives x dot is equal to what? Now the scalar is lambda exponential of lambda t, okay? It's c times lambda exponential of lambda t, okay? But from the differential equation, we know that x dot must be equal to ax. But x dot computed before is lambda exponential lambda t times vector c. And ax is equal to a times, we conjecture a solution x of this type, c exponential lambda t, okay? We conjecture this. So it must be equal to c exponential lambda t. Now here there is exponential lambda t, which is a common scalar that multiplies both sides. So what we get is that if our conjecture is true, then lambda and c is C1, C2, okay? Lambda and c must be such that lambda times c is equal to a times c. And this means that our conjecture works, provided that this is a matrix A, okay? Lambda is an eigenvalue of matrix A, and C is an eigenvector associated to eigenvalue lambda, okay? So the idea is, okay, this is an important result. Our conjecture works. Conjecture means there exists a solution of the type vector c times exponential of lambda t for some lambda and some vector c. Our conjecture works, provided that lambda is an eigenvalue of A and C is an associated eigenvector. Okay? This is the reason why it is so important. Eigenvalues are so important for the dynamics. And the reason can be, the intuitive reason is this one. What determines the joint dynamics of these two variables? Matrix A, okay? But matrix A is not like in the simple case of an equation, a coefficient A, okay? Coefficient A is easy to understand because we have, okay, in this case, what determines everything is this coefficient A. It determines whether the steady state, which is 0 in this case, is stable or unstable. If it is positive, it is unstable. If it is negative, it is stable, okay? You see from this. And A that appears here, we are in a one-dimensional world. A that appears here is the same coefficient that appears in the equation here. But now we have a matrix, and the matrix is something with more structure, okay? It depends on the elements here and where they are, the position of the elements. But all these four elements jointly determine the evolution of both variables. So there is some information that we can extract from these elements, which plays the same role of A in the one-dimensional equation. This information is the eigenvalues of the matrix, okay? We see that, for instance, if the eigenvalues are negative, we have stability. If the eigenvalues are positive, we have instability. If they are one negative and one positive, we see a new type of stability, which is called saddle path stability. So this is basically the idea. Now I go back to the slides. So let me just, here is everything I have explained in the other slide. Okay, and now there is an example, and I'm going to show you this example. First, let me just disconnect for a moment this one, just for a moment. Let me check the situation here. Okay. I predict that it will take longer than expected. Okay, so let me just continue. Okay, now here. So this is what was written in the previous slide, basically, the summary. Example. Now, the point is that don't get confused about, we are not stating that all the solutions are of the type that corresponds to our guess. If there exists a solution, my question was whether there exists a solution of this type among the infinitely many solutions. So it can be shown that, for instance, if the matrix has two eigenvalues, both are solutions, okay? Both of them are solutions. But then it can be proven very easily that also their sum is a solution. Not only their sum, any linear combination of these two basic solutions is a solution. So it is very easy to build the solution, the full solution, it's called the general solution, to this system. Now, consider this simple example. The matrix is 1/6, 1, minus 1/3, minus 1. X dot is equal to AX. I write down the system. X dot 1 is equal to 1/6 X1 plus X2. So what we see here is, for instance, that the variable X1 increases over time with a direct dependence. So let's say the size of the derivative depends directly on the size of X1 and the size of X2. But for the derivative of X2, this decreases over time proportionally to X1 and to X2, okay? So the joint behavior is this one. So we want to see what happens in the long run, for instance, okay? The eigenvalues and associated eigenvectors of the A can be computed by the short formula lambda squared minus trace of A. The trace is just 1/6 minus 1. It is minus 5/6. So minus trace is 5/6. The determinant is 1 minus 1/6 plus 1/3, which is 1/6. This is a very simple second-degree polynomial. The two rules of this polynomial are minus 1/2 and minus 1/3. So we have two eigenvalues for this matrix. They are both negative, okay? We now know that there will be a solution of this type. Let me just, before showing this, we have minus 1/2 and minus 1/3, okay? So we know that based on our previous reasoning, we know that C1 to be determined, but that will be an eigenvector, times exponential of minus 1/2 t will be a solution, okay? Because we have lambda 1 here, and this will be eigenvector associated to minus 1/2. But there will be infinitely many such eigenvectors, okay? But we also know that C2, this is a vector, C2 exponential minus 1/3t will be a solution. And this is an eigenvector associated to lambda 2. Lambda 2 is minus 1/3, equal to minus 1/3. But if these are two solutions that correspond to our guess, and they are actually solutions, also their sum, okay, is a solution, and also any linear combination of the two. So I could multiply this by alpha and this by beta. But I don't need to multiply by alpha and by beta because C1 and C2 are by definition arbitrary vectors that correspond to a constant times a prototype vector, okay? Because you know the eigenvectors can be represented by alpha times a given vector or beta times another vector, okay? And remember the first example. So we don't need to put this here. This is already a linear combination of two basic solutions corresponding to the two different eigenvalues. Of course, should be clear that this works only when we have two real and distinct eigenvalues. So our polynomial has two real solutions and they are distinct. Remember the second degree equations, okay? There are three qualitative cases. Real and distinct solutions, real solutions two real solutions that collapse into a unique number, and two complex conjugate solutions, okay? When basically the equation has no solution for real numbers, okay? They are complex conjugate. Okay, we are dealing only with the case of two real and distinct eigenvalues, okay? The case of one is a kind of degenerate case that can be studied. It's not difficult, but the formula is different. And for complex eigenvalues, the formulas involve trigonometric functions, okay? So we don't, we just show one thing about qualitative analysis of this, but I don't want to write the solution in the complex case. Only in the real distinct case of eigenvalues. Case of real distinct eigenvalues. So this is the basic idea. So this is already the general solution to our model. So basically, I find these two eigenvalues. I have to find the eigenvectors associated to the first one, the eigenvectors associated to the other one, and then put them together into the solution formula. So what are the eigenvectors associated to the first eigenvalue, lambda 1? Lambda 1 was minus 1/2. So lambda identity minus a is this one, like the previous exercise, times x1 x2 equal to 0, 0. Lambda 1 is minus 1/2, so if you put minus 1/2 here and here, you get this matrix. If you write down the system, you obtain minus 2/3 x1 minus x2 equal to 0. And the second equation is 1/3 x1 plus 1/2 x2 equal to 0. Okay, so basically is this is the previous equation. The second equation is the previous equation multiplied by minus 1/2. Okay, so it's proportional to this one. So this doesn't add any information to what is already stated by the first equation. What we get is x2 from this one, for instance, x2 is equal to minus 2/3 x1. How can I write the whole set of solutions? The second term, the second component must be minus 2/3 the first component, so the the simplest possible vector satisfying this is, for instance, 3 minus 2, okay? Second component is minus 2/3, the first one, then multiplied by alpha, okay? This is our C1 to be associated to the first eigenvalue. If we do the same with the second eigenvalue, which is minus 1/3, we do the same, we compute lambda 2 identity minus A, we solve the system, and we obtain, you see here, now this is multiplied by minus 2/3. The second equation is the first equation multiplied by minus 2/3, so it is proportional again. x2 is equal to minus 1/2 x1, so second component is minus 1/2 the first component. This is the second eigenvector, and this is the general solution. C1 alpha, now for simplicity, alpha can be also called C1 for analogy with the arbitrary constant of the solution, okay, of the differential equation, but I can leave it expressed as alpha, doesn't matter. So it's basically the first alpha times 3 minus 2 exponential minus 1/2 t plus beta, or if you like C2, times 2 minus 1 times exponential minus 1/3 t. So this is our solution. We have a solution, a general solution that depends on two arbitrary constants. For a scalar differential equation, so a one-dimensional differential equation, we have a general solution that depends on one arbitrary constant. Here we have a system of two equations, and the solution depends on two arbitrary constants. We have a system of n equations, the solution depends on n arbitrary constants. Okay? Why 2? Because if I want to obtain a particular solution, I have to specify the initial value of both variables, okay? So I need two constants. So let me see if there is some remarks or question in the chat. Okay, I don't know what this means, but anyway. Okay, so let's do that. If now it happens that I had to interrupt this will be the break, basically, okay? So this will be already the break. It depends on, I don't know, because discussions always take longer than expected. So sometimes they are useful, sometimes they are not. So what happens here? Look, it's very easy now to see what the behavior of this solution is as time tends to plus infinity. Now, for instance, the first remark is that the general solution now for each variable x1 and x2, we have a kind of mix between two exponential functions, okay? But the important point here is that both the exponent have a negative coefficient here. So if t tends to plus infinity, what happens to these solutions? Both variables converge to 0, okay? And remember, in our simple one-dimensional equation where the solution is of the type xt is equal to c times exponential minus at, and a is positive, okay? So this is a negative quantity, and xt tends to 0 as t tends to infinity, okay? And the same happens here. The same happens here. So the condition for this to happen in a two-dimensional case is that both eigenvalues are negative, okay? If both eigenvalues are negative, this in the long run, both variables tend to 0. 0, by the way, is the steady state of this simple homogeneous system. 0, 0. Both variables at the level 0. Now, what happens, for instance, if we get a solution like this, but with the two exponents here are positive, both positive? Both variables explode in the long run, okay? Because we would have an exponential with a positive exponent here, exponential with a positive exponent here, and the same here. And in the long run, both explode. Even if here you have, if here you have, also if you have plus and minus, the final outcome is explosion, okay? Because they are exponential with different exponents. And in the long run, the one with the larger exponent prevails. So they will both explode in the long run. But what is important is that in the case of negative eigenvalues, if all the eigenvalues are negative, we have stability. So what happens in the case a non-homogeneous case in which B is not 0? It's AX plus B. Here there is should be underlined, okay? It's a vector. X dot is equal to EX plus B. So we take the same A as above, but there is a vector of forcing terms, which is -4 and 5. So the system will be like this. The part up to this point is the previous system. But then we had -4 in the first equation and +5 in the second equation. If you remember, the structure of the solution, which you already found in other cases, is the general solution to the associated homogeneous system plus the steady state. Okay? So it's easy to find the general solution to this system because it is the sum of the general solution to the associated homogeneous system, which we already know. It is this one. Okay? Plus the steady state. The steady state is the constant solution to this system. What is the meaning of constant solution to this system? Both variables at the steady state must be at constant levels. Okay? Both variables, not just the unique variable, both variables. And this means that their time derivatives, both at the same time, must be 0. So how can we find a steady state? Set simultaneously equal to 0, both x dot 1 and x dot 2. Both variables must be stationary, must not change over time, so their level must be constant. Set them equal to 0, it becomes a trivial system in two equations and two variables. This is an algebraic system, so we can just, for instance, by substitution or by any other method, Cramer's rule, matrix inversion, and so on and so forth, we can just solve the system and find the steady state. Okay? So here the solution is one in which at the steady state, so there exists a constant solution in which x1 is at the level 6 and x2 is at the level 3. Okay? Break. Okay? Pronto? is that this is, of course, the general solution, okay? This is the, try to, for the moment, no, I cannot leave the slides here, but if you can just write down the solution here, which is already, you already have the slides, right? You have the slides. There is a solution, and we have the steady state, which is this one. Okay, so this is the solution to the previous homogeneous case. Now I add the steady state. Okay, is that clear? The homogeneous solution plus one particular solution. So this is, but now we have some arbitrary constants that do not tell us much about their meaning. Okay, we would like to relate them to the initial values of the variables, and we can do that because if we impose that, for instance, x1 at the initial time is 2 and x2 at the initial time is 1, we can specify the variables c1 and the constant c1 and c2 in a way that the initial condition is satisfied, okay? Like for the case of one-dimensional equations, but in this case we have two variables, so we have two initial conditions, and I can ensure that the two initial conditions are satisfied by playing with two arbitrary constants, okay? So you see very easily, just solve a linear system. You see very easily that C1 is equal to 8 and C2 is equal to minus 14, okay? You just impose that at time 0, so put t equal to 0 here. The first equation, x1 of 0, which is this one on t is 0, is equal to 2. And the second is equal to 1, okay? Now I have to interrupt for a few minutes because I have to attend a crucial part of a department meetings, but I will be back in, let's say, 10 to 15 minutes, just moving to the other room. And you can stay here and try to work out this example. Now, next I will show you also the graphical representation of this, okay? Okay, so let me just do this. and see something more about these dynamical systems. Let me join again the group. Okay, so let me share the screen. Okay. So I wonder whether things are okay up to this point. So this is the solution to the associated homogeneous system. If I add the steady state, which means adding the steady state values of both variables respectively to the two parts of the solution, okay? And if we impose a particular solution, we find basically two values for the two constants, 8 and minus 14. Okay, is that clear what we do here? X1 at time 0 is equal to 3C1, because this becomes 0, plus 2C2, okay? Plus 6. And this must be equal to 2. This is what we impose. X2 at time 0, which is equal to minus 2C1 minus C2 plus 3 from the solution, must be equal to 1. This is just a simple linear system into equations and two unknowns, C1 and C2. You can write this in this way and solve either by substitution or by just using the Cramer's rule or the matrix inversion method, and so on and so forth. So it's C1 equal to 8, C2 is equal to minus 14. What is that? Is that the last? Okay, it is the last slide. So I would like to show you. So what do you think would happen in the long run? As t tends to infinity, remember the previous model without these 6 and 3 components here had 0, 0 as the limit, okay? Now, if t tends to infinity, this becomes 0, this becomes 0, this becomes 0, this becomes 0, and in the long run, the two variables converge to the steady state, okay? 6, 3. So just to show you what happens, I would like to show you just once this, representation of the solution. Here I wrote variable x1 of t already. Now we write variable x2. So what happens here is that if I replace to C1 8, this becomes 24 C1 minus 28 C2, because C2 is minus 14. Okay, so this becomes, 24 C1 minus 28 C2, respectively multiplied by these exponential factors, plus 6 is equal to x1, okay? x2 is, it is minus 2C1, so minus 16, exponential minus 1/2 t, plus 14, exponential minus 1/30, plus 3. Well, let me just write also this one, x2 of t is equal, it was, if I'm not wrong, it was minus 16, was the coefficient of the term exponential minus 0.5 t. And then, if I'm not wrong, it was plus, it was plus, so minus 16, which minus 2 times 8, plus 14, exponential minus 130, plus 3. So let me finish here. Plus 14, exponential minus t over 3, plus 3. So you see, of course, this is, here are the two initial conditions. So you see that the first variable x2 has the initial value 1, okay, 1, while variable x1, the red one, has the initial value here 2, okay, which was precisely the initial condition that we imposed before. Okay. In fact, this solution that we found satisfies the initial condition, and it is interesting because you see that the two variables, if you move this, you see the two variables have some evolution which is non-monotonic initially, with some adjustment, okay? And this depends on the joint interaction of the two, but in the long run, what prevails is the steady state levels, okay? So the first variable settles on the value 6 here, and the other variable tends to converge to the value 3, which is the steady state, okay? So this is basically what, of course, this part with negative t doesn't matter for us. We start here at 0, okay? So this is a typical example of two variables that evolve jointly according to some mix of exponential functions, okay? It's a kind of linear combination of exponential functions for both. But even more intricate movements arise when, you see here, we have both are negative, both coefficients are negative. But suppose that one is positive, one eigenvalue is positive and the other one is negative. So what would happen? Which one would prevail, okay? Of course, what prevails is the positive one, because the negative one makes the corresponding term to converge to 0, okay? So what prevails in the long run is the positive coefficient. Anyway, also when one is negative and the other is positive, there is some kind of stability, some very special case of stability, which is called saddle path stability, which is what I'm going to show you in the next slides. So basically, there is nothing new except that we have a new type of a new example of a dynamical system in which one eigenvalue will be positive, the other will be negative, and I'm going to show you what will happen in this case. Okay. By the way, saddle path stability is the most common type of stability in continuous time models in economics. Okay, so the next slide is about saddle path stability and qualitative analysis. This one. Now, consider this example. The structure of the coefficients in this coefficient matrix is very typical of many models. We have a first variable x, now I don't call them x1, x2, I call them x and y, okay? X of t has a time derivative which is 1/2 x plus 3/4y. So this depends positively on the levels of both variables, minus a constant here, which then will be set equal to 10. The second variable, y dot, depends positively on x, but negatively on y itself. So if you write down this system in matrix form, what you see is 1/2, 3/4, 1 minus 1/2, which is a coefficient matrix. And the vector of the constant terms is minus r for the first equation and 0 for the second equation. We know, first of all, let me find the steady state solution, and next, let me find basically the general solution, which means basically finding the solution to the associated homogeneous system and then taking the sum of the two. The steady state solution generally satisfied x dot equal to 0. This is just, you don't need to know the structure of the steady state solution, the general form for the steady state solution, but what I mean is that if I have a general system written in matrix notation, for instance, x dot equal to x dot vector ax plus b. Remember that everything can be written in matrix form, okay? So if I set x dot equal to 0 vector, I set all the time derivatives simultaneously equal to 0, I have an algebraic equation in the levels x, which is what I need to find the possibly constant solutions to this system. So I have a times x is equal to b, to minus b, okay? Because I have ax plus b equal to 0. Now, assuming that a is invertible, so the determinant of a is different from 0, I can left multiply by its inverse, both sides. Here I get minus a minus 1 times b. So x star, the steady state solution, is just minus the inverse of matrix A times b, the vector of the first two terms. This is the general formula for the steady state solution. Of course, since we will deal in practice, I want you to see this formula, but in practice, since we will deal with two-dimensional systems, it will be also easy to find the steady state by just substitution or Cramer's rule. But remember that there is a general formula for the steady state of a linear system, okay? Now, let me find the steady state to this model. If I set simultaneously x dot and y dot equal to 0, this means that I'm imposing 1/2 x plus 3 over 4 y minus r equal to 0, that is 1/2 x plus 3 over 4 y equal to r, and x minus 1/2 y equal to 0. Very easy to find the solution by substitution. Y star is r, x star is 1/2 r. For instance, if r is equal to 10, x star is equal to 5, y star is equal to 10. This is our steady state. Now, let me find the eigenvalues. I don't build matrix lambda identity minus 8. I use the short formula. Lambda square, I write down directly the characteristic equation, okay, which is lambda squared minus trace of matrix A times lambda plus determinant of matrix A. The trace is 0. Very easy. You can see that the trace is 1/2 minus 1/2, 0. So there is no term in lambda. It's a very easy equation. Plus determinant of A, which is minus 1, because it is minus 1/4 minus 3 over 4, so minus 1. So the characteristic equation becomes lambda squared minus 1 equal to 0, and the two solutions are plus 1 and minus 1. One eigenvalue is negative, the other eigenvalue is positive. For the eigenvectors, we impose in general that lambda identity minus A times x is equal to 0. Okay. Of course, if we replace either minus 1 or plus 1, we get something here, and you write down the system, we get a redundant equation, okay? Two equations that state the same property. For instance, by substituting for lambda 1 equal to minus 1, I get these two equations. The second equation is the first equation multiplied by 2/3. And from this equation, I can use, for instance, this equation, because the two equations are equivalent. I use this one. So x2 is equal to minus 2x1, means the second component is minus twice the first component. So this is the usual way to write the associated eigenvector. If we do the same with the other eigenvalue 1, I get this. So minus x1 plus 3 over 2 x2 is equal to 0, x2 is equal to 2/3 x1. Okay, so one typical vector of this family is 3, 2, and then I multiply by an arbitrary constant theta. So this is the eigenvector, the set of eigenvectors associated to lambda, the eigenvalue 1. This is the set of eigenvectors associated to the eigenvalue -1. Nothing difficult from the point of view of writing down the solution. The two constant terms are the steady state coordinates 5, 10. I can write down the general solution. Okay? Xt is equal to alpha, if you like, times the eigenvector 1 minus 2, times exponential, this is the eigenvalue -1 times t, plus beta, or C2, times, here I wrote the eigenvector in a different way, instead of 3, 2, 1, 2/3, for instance, okay? Which is the same. Why is it the same? Writing here 3, 2, or 1, 2/3 is exactly the same, because C2 is an arbitrary constant, okay? It's arbitrary. Of course, when you then impose the initial condition, everything results in the same equations for the two paths, independent of what you choose as the prototype eigenvector, okay? But when you write the general solution, you can use any. Here you could use 2 minus 4, or -1/2, 1, for instance, plus x star, y star. So this is a typical case of saddle path stability of the steady state. You see, the two, it is not fully unstable because one eigenvalue is negative, the other one is positive. If also this one was, for instance, positive, then of course, as t tends to infinity, you would see both terms exploding, okay? But one is negative and the other one is positive. So what happens in the long run? This is a point which is important to stress this point. What happens as t tends to infinity? I would say everything explodes for a simple reason. This goes to 0. This goes to infinity. As t tends to infinity. Plus infinity or minus infinity depending on C2, okay? So I would say this explodes. This is not completely true, because everything explodes unless we start from some set of initial conditions such that C2 is equal to 0. Okay? Because if C2 is equal to 0, the effect of the positive eigenvalue is completely cancelled. If C2 is equal to 0, 0 times a term that increases exponentially is 0. In this case, we would have convergence to the steady state. Okay? So the basic insight is that in this case, where we have two eigenvalues with opposite signs, trajectories will diverge, except those for which C2 is equal to 0. And those trajectories corresponding to a case where C2 is equal to 0, which means the set of initial conditions that correspond to the case C2 equal to 0, are called saddle path, or stable arm, or stable set, or stable manifold of the dynamical system. Okay? So this is a type of stability that we don't have in one-dimensional systems. In one-dimensional systems, we either have explosive behavior, exploding behavior, or convergence to the steady state. Here we can have this mixed behavior, which is called saddle path stability. So this is a very easy way we can find this set of initial conditions. We have to start from the desired result, okay? So put C2 equal to 0 here in the equation of the solution. If C2 is equal to 0, so we write the solution, it becomes like this, okay? Now, move the steady state part to the left and change the sign. You see that the deviation of x from its steady state level is equal to C1 times 1 times exponential of minus t, okay? And the deviation of y from its steady state level is equal to minus 2 C1 exponential of minus t, okay? But if you go back, here to the behavior of y, it's minus 2 times this quantity circled with red, but this quantity circled with red is just this one, is xt minus x star, okay? So you can replace here xt minus x star. So you get y minus y star is equal to minus 2 x minus x star. This is called transforming a system which is written in parametric form into a system in which y and x are related to each other by a relation in the plane xy, okay? You see here, these both depend on t. But you can eliminate the dependence on t and relate x to y, and you get this. Remember that x star is 5, y star is 10. Replace 10 here, 5 here. This is the equation of a straight line. We can write the equation of the straight line in the usual form. Y is equal to minus 2x. That would be plus 10, and then again plus 10, plus 20. Okay? So this is the equation of the saddle path. Why? Because suppose that you select x, given, whatever you want, but you select y at time 0, you select x, any value, but once you have selected x, you select y equal to minus 2x plus 20. Okay? This means that they are along this straight line, but this means that they satisfy the condition C2 equal to 0. So for this particular initial condition, the term with the positive eigenvalue will be uninfluent, okay? Because it will have C2 equal to 0. Because we started from the desired result in order to derive this straight line in the plane. This is called the equation of the saddle path. So what happens here is like this. Basically, the equation of the saddle path is y equal to minus 2x plus 20. We represent this in the plane xy. Remember now, we don't have any more the dependence on t. We can guess what happens as t increases. But here in this graph, we have only the behavior of y, a second component of our state vector, as a function of the behavior of x. This is a straight line, the red one is a straight line of equation, y is equal to 20 minus, what was that? That was 2x, minus 2x plus 20. So the red straight line is the saddle path, okay? If you start at any point along the saddle path, the behavior will be that of convergence to the steady state. This is a qualitative diagram similar to the one-dimensional diagrams for one-dimensional systems in which we have the arrows of motion, okay? The arrows of motion are reminiscent of the existence of time that increases, okay, that evolves, but we don't see functions of time here. We see y as a function of x. Basically, the two variables will move along the saddle path and they will converge to the steady state. But there is another object in this plane, which is called the unstable set. The unstable set is the green line. And the green line can be obtained in a very similar manner from the system. Don't eliminate the term in C2. Eliminate the term in C1. Eliminate the term that produces convergence, okay? If you set C1 equal to 0 and you repeat the same experiment, set C1 equal to 0, you have that your system is like this. Move X star and Y star to the left again. Okay? So you see that Yt minus Y star is 2/3 Xt minus X star. Okay? Because this is Xt minus X star. Replace, you have another straight line. Y is equal to 2/3 X plus 20/3. Look what happens here. You get the green line. If you start from any initial condition along the green line, you have movement away from the steady state, from one direction to the other, which is linear in the phase plane, in the plane xy, okay? So you have two extreme behaviors. One, which is where you have a kind of perfect convergence to the steady state, if you start on the saddle path. And one in which you have, let's say, I would call it perfect divergence from the steady state, in the sense that the movement is along a straight line in the plane away from the steady state. For any other initial condition, for instance, if you take an initial condition here, you see, you can represent the solution, okay, for this system, like I did before. You see something that in the plane goes like this. It looks like it approaches the steady state for a while. I don't know whether you can see the hand. Suppose that you start this. It looks like you approach the steady state for a while, then it turns along the unstable arm, and then in the long run, it diverges along the unstable arm, okay? So this is the typical saddle path behavior. Also, if you start here, you see, for instance, some kind of initial movement towards the steady state, but then it goes away in this direction, okay? So this is typical of the saddle path stability. This is typical of saddle path stability. Okay, so what I mean now is that, of course, you may see models of continuous. I don't see whether you have already seen a qualitative diagram like this in economic dynamics. Never? Anyway, many economic models, not only linear like in this case, but non-linear, are studied by means of these qualitative diagrams, just to figure out what the behavior, qualitative behavior of the variables would be. And what I mean is that in many economic models, this is just to let you understand why it is important. In many economic models, there is, for instance, one of the two variables, for instance, y, which is typically a stock variable. So basically, at time t, cannot be selected by the decision maker. For instance, the capital stock in an economy, I mean, you can try to increase the capital stock in the future, but at time t, you cannot change. The capital stock depends on the previous history, okay? So this is called, it is a stock variable. And it has some level, so for instance, 15 here, okay? Stock variable is at the level 15. But the decision maker has a flow variable, which would be, for instance, x in this model, okay? And the flow variable can be controlled by the decision maker. So for instance, if the flow variable is the level of consumption or the level of investment at a given point in time, I can decide the level of investment, right? So for a given level of the variable y, for instance, that would be along this line of this level, I can select a particular value, that would be here. I can select a particular value for x, which is under my control, such that the system falls on the saddle path. So this is the basic idea in many models, okay? There is a stock variable. But if I select the flow variable in a way that xy is on the saddle path, the system will converge to a steady state in the long run, okay? So this is the basic idea. So from a mathematical point of view, it's very unlikely that the point is exactly on the red line. But from the economic point of view, in which one of the variables is under the control of a decision maker who knows the model, because remember that economics, the concept of rational expectations in economics is pervasive, okay? It's everywhere, okay? Representative agent and rational expectations, which means basically model knowledge from the part of the decision maker. If the decision maker knows the model, decision maker can select the flow variable in a way that the point, so the system is on the saddle path, and in the long run we will have convergence to the steady state. This might seem strange, but it is a common assumption in many models. There is another reason, because in dynamic optimization problems, if you are not, solutions that do not start on the saddle path cannot be optimal, okay? In the sense of dynamic optimization. So if the decision maker is optimizing the objective functional, its flow variable will be such that the economy is on the stable arm. So this is just a digression to let you know why this quite strange type of stability in mathematical terms, because it is very unlikely, is the common case, is the standard case in macroeconomics. Okay? Anyway, now there is something about a qualitative analysis, but I would like to stop for a moment. I will show something about this tomorrow before showing you, let's say, summary exercises. I would now try to show you something else, which is an exercise on matrix operations, because as I explained once at the beginning of the course, the purpose of this course is twofold. First of all, I want to show you something about dynamic analysis, and we use matrices in dynamic analysis, especially eigenvalues. Second, however, I was explicitly required by colleagues of mine, okay, to show you, to give you some training in basic matrix operations, which then are useful for econometrics, for instance. So a part of this and a written exercise of the examination could be something about matrix operations, okay? Matrix operations are not just application of, let's say, rules, computational rules. Also require the knowledge of some theory. Because if you know the theory, you can see that there are different methods to compute the result of your exercise, and also to check the result of your exercise and to figure out the meaning of your results. So let me just show you a very basic exercise on matrix operations, very basic review exercise on matrix operations. Suppose that we have these two matrices, AB, vector x is x1, x2, and vector b, this is uppercase B, is a matrix, vector b is 2 minus 2. So the exercise requires to compute the determinant of A, the inverse matrix of A minus 1B, AB, and X transpose times B transpose times A transpose, AX, A transpose times A, X transpose times A transpose times A times X, and A plus B squared, okay? So be prepared to solve these types of exercises. This only require, apart from being able to solve them in elementary terms, which means being able to perform a matrix product, okay? Understand what is the meaning of this 1, 2, 3, 4 products, okay? Also knowing some theory, because if some of the results can be exploited later, if you know some theory, okay? So the first Question, determinant of A, of course, the determinant of A is 3 plus 2 equal to 5. Now, matrix A minus 1. So this is also a review of the basic rules, okay? Matrix A minus 1, it is the inverse of A. We know that the inverse of A exists because the determinant of A is different from 0. And the necessary sufficient condition for a square matrix to have an inverse, a unique inverse, is that the determinant is different from 0. Next, the formula for the inverse matrix is 1 over the determinant times a new matrix in the two-dimensional case, remember, and the new matrix is obtained by exchanging the two elements in the main diagonal and taking the negative of the remaining elements. So it becomes 3, 1, and then here minus 2 and here 1. Okay? Oh, can we check the result? Suppose that, okay, you remember the formula, you compute the matrix. Can we check the result? Of course, because the matrix, apart from the formula to compute the matrix, the inverse matrix has a meaning. It is the unique matrix that multiplied by A gives the identity matrix as the result. So if you take this matrix, you can neglect this constant term 1 over 5 here. If you take this matrix and you multiply this matrix by the original matrix, you should obtain this scalar matrix, okay? In such a way that if you then multiply by 1 over 5, you get the identity matrix. So we can check the result here, and of course, what we get is this scalar matrix. So our computation was correct. This is actually the inverse matrix of A. A minus 1 times B. Of course, we have A minus 1. We can multiply A minus 1 by the vector B. Okay, let's do that. A minus 1 is this, times B. My suggestion is that you don't use the scalar. This is the product of a scalar by a matrix. Just use the scalar in the next solution step, in the last solution step, not immediately. So in general, computations are easier. So you get here the vector, the solution vector is again 1 over 5 times 6 plus 4, 10, 2 minus 2, 0. Okay, so the solution vector is 2, 0. Is there any way to check our result? Yes, because this product has a meaning. This is the matrix form in which we can write the solution to a linear system, which is AX equal to B. So the system AX equal to B as if A is squared with a non-zero determinant, if A is invertible, this has a solution which is X is equal to A minus 1 times B. So if we want to check the solution, we can just write down the system AX equal to B. Matrix A is this one, so it is x1 plus 2x2 equal to 2. Minus x1 plus 3x2 equal to minus 2. Write down the system, solve the system manually with elementary methods, and you get the solution. So our computation is okay. A times B, okay, just the matrix product. The two matrices are A and B, and the result is minus 1, 5, 1, 5. Remember that the product between matrices is just row by column. For instance, this element in position 2, 1 is the product of the second row of the first matrix times the first column of the second matrix. 2, 1. Okay? Now, X transpose times B transpose times A transpose. Suppose that you want to compute X transpose times B transpose times A transpose. Remember that in the product between matrices and vectors, the associative property holds. So you can just compute this first, and then left multiply by x transpose. Remember that x transpose is this one. It's a row vector with the two components of x, which was initially defined as a column vector, okay? But this one, if you remember the properties of transposition, you remember that if you have the product between two matrices and you transpose the result, you have the product between the transposed of the original factors, but with the reverse order. So this is just A times B transposed. Okay? Clear? But also now we know that what we want to compute is x transpose times A times B transpose. This is the product of two matrices. I can call it C. Okay? So it is equal to x transpose times C transpose. Anyway, x transpose times C transpose again can be regarded as C times x transpose. But C is A times B, okay? So basically, we know that what you want to compute is A, B, X transpose, okay? So this is what we want to compute. This one is the transpose of ABX, okay? And so we can, if you know something about these properties, we can exploit the previous results, for instance, because we do have A times B. It's very easy to compute A times B transposed, okay? I mean, we know already what is A times B, so we can use A times B multiplied by X and then transpose the final result, okay? So A times B is minus 1515 times X, and the result transpose. Okay? So it becomes minus x1 plus 5x2. Remember that the result here is a vector, which is a column vector. The first component is minus x1 plus 5x2. Second component is x1 plus 5x2. Column vector. But now we have to transpose it. So it is equal to minus x1 plus 5x2, row vector x1 plus 5x2. Okay? Row with two components. So this is the result of our problem. Of course, as an exercise, you can build the transpose of A, the transpose of B, and then try to compute directly this result. Okay? Now, A times X. Okay, A times X is very easy. A is this one, X is this one. So x1 plus 2x2 minus x1 plus 3x2. It's a two-dimensional column vector. A transpose times A. A is this one. I put A here. I left multiply by its transpose, replace the rows with the columns. So it is first row 1 minus 1, 2, 3. Make the computations, it's a matrix product, and you get 2 and 13 in the main diagonal, and as expected, the same element in the other positions, minus 1, because you know that the product between a matrix and its transpose is always a symmetric matrix, okay? So when you have the product between a matrix and its transpose, it's always a symmetric matrix. By the way, also if you multiply A times A transpose, so you invert the order of the factors, you get a symmetric matrix as the result, but it is not the same as this one, okay? Because they don't have the commutative property. Now, suppose that you want to compute X transpose times A transpose times A times X. Okay, you want to compute X transpose times A transpose times A times X. Remember that you do have the associative property, so you can group the products as you like, provided that you don't commute. So, for instance, I can do this, which is the easiest way to compute. Because I already know AX, we know AX is equal to a column vector, which we already computed before, and AX is equal to, it's here, sorry, x1 plus 2x2 minus x1 plus 3x2. But this is nothing but AX transpose. Okay? So our product results in x1 plus 2x2. First component of the vector, minus x1 plus 3x2. And this is AX, let's say, transpose, okay? First vector times this. What is the result? The result is x1 plus 2x2. This is a product of a row vector by a column vectors. The result is a scalar, 1 by 1 matrix. x1 plus 2x2 squared plus minus x1 plus 3x2 squared equal to x squared 1 plus 4 x squared 2. The mixed term is 4 x1 x2 plus x squared 1 again. This becomes minus 6 x1 x2 plus 9 x2 squared. Okay, so the result is just that you have to take the sum of the terms in x squared, in x1 x2 and in x2 squared, and you get this. This one, 2 x squared 1 plus 13 x squared 2 minus 2 x1 is 2. Okay, but you can also, I want to point out that you can also solve the system by grouping the terms in a different way. X transpose times A transpose times A times X. So if you call, I don't know, B, or no, not B, but D, this matrix, A transpose times A, this will be a symmetric matrix, of course. And you can compute this also in this way, because we already know this matrix, which is this one. So the structure of the computation in this case is X transpose times the symmetric matrix that we obtained as the result of A transpose times A times X, okay? And this is the typical way in which we write a quadratic form, which you should remember from the first part of the course, a quadratic form, which is a quadratic expression in variables x1 and x2 in this case. Okay, so you can do this in two different ways. Either you multiply this row vector by the result of this product, or you multiply first the row vector times this, and then the result times x1, x2 column vector. In any case, you get the same result here. And I want to point out here that this way of computing the quadratic form is let's say, the standard one if you have the symmetric matrix here already, which we have in our exercise. It is A transpose times A, because you look at the coefficients. The coefficient of the term x squared 1 is here, coefficient of the term x squared 2 is here, And this -2 of the mixed term is the sum of the two remaining coefficients, okay? So this is basically two different ways to compute this this X transpose A transpose AX in our exercise. The other exercise, the other question was the squared of A plus B. The squared of A plus B is a matrix, 2 by 2 matrix, just obtained by adding A to B. If you add A to B, adding two matrices with the same structure means adding the elements one by one. So it's matrix, the sum of matrices occurs element-wise, so element by element, okay? So for instance, the term in the first position is 0, the one in the second position here is 3, and so on. So you have the sum. Computing a square of a matrix means multiplying the matrix by itself, provided that it is squared, okay? So you multiply the matrix by itself and you obtain this one. Okay, -3, 15, -5, 22. You can check by exercise that the result of this squared is equal to the square of A plus the square of B plus AB plus BA. Of course, it is not equal to A squared plus 2AB plus B squared, as for numbers, just because AB is not equal to BA for matrices. So if you want to check your result, just compute A squared, B squared, these two products. One of them is already there because it was part of the exercise. Then you take the sum of all these terms and you should get this one again. Now, there is another thing I want to show you. Final question here for this exercise. We do have a matrix B here, so find a matrix of the unique matrix C satisfying C times B squared is equal to identity, in this case of order 2, of course. So matrix B is this one, -1, 1, 0, 2. B is -1, 1, 0, 2. What is B squared? B squared is equal to -1, 1, 0, 2 times -1, 1, 0, 2, which is equal to 1. And this becomes 0. -1 plus 2, which is again, if I'm not wrong, this is again 1, 0, and then 0 times 1, 0, 2 by 2, 4. Should be this one, B squared, okay? B squared is this one. Now, finding a matrix such that C times B squared is equal to I2 means that C is equal to definition. So this is the definition of inverse matrix. Should be the inverse of B squared. Okay? So our matrix C is just the inverse of this one. The determinant is 4, so 1 over 4, and then exchange the two elements in the main diagonal, 4, 1, change the sign to the other elements. Okay? Here is our matrix C. Now we wonder whether, and this is the last comment, the last insight for today's class. Here is the meaning of this notation. Just try to understand the meaning of the notation. -1 denotes the inverse matrix of something. It's not raised to the power -1 for matrices, okay? But, so this is the inverse of B squared. We know what B squared is, and we compute the inverse. But we wonder whether this could be interpreted in the usual way we know for powers for real numbers, okay? So, powers for real numbers have properties. For instance, a real number B raised to the power of 2 and then raised to the power of -1 is the number B raised to the power of -2, okay? So can we denote this as b to the power of -2 in the usual sense of powers that we know for real numbers? And the answer is yes, because you can check that the inverse of matrix B squared can be written as b to the power of -2, which is basically the inverse of b times the inverse of b. If these are numbers, b to the power of -1 times b to the power of -1 is b to the power of -2, okay? You sum this one. It is exactly the same. So by exercise, compute b minus 1, the inverse of b, multiply it by itself, and you will get again the inverse of b squared. So we can, if we call this b to the power, denote this as b to the power of -2, it's well defined. It has a strong meaning, I mean, because it satisfies this property, okay? So this is the same as for numbers. So this is to conclude that for matrices, we also have negative powers that have basically the same meaning as for numbers, with the same properties between powers of matrices. So b to the power of -3 times b to the power of 6 is equal to b to the power of 3. Okay? Like for numbers. Okay. I think that's all for today. Tomorrow, just let's say something more about qualitative analysis of linear systems of two differential equations, and then review exercises. We already had a review exercise for matrices here, so tomorrow review exercises for integrals and dynamical systems. Integrals and differential equations and difference equations, okay? Tomorrow morning. And also tomorrow morning, it is the last chance we have to, for the so-called students' opinions, okay? So tomorrow I will just use the break to provide you the code for the students' opinion for the course, okay? That's all. Thank you. I'll see you tomorrow. Okay, for the examination, okay, if you want to see your, the reasons for your grade, so just send me an email, I send you the, and also I will, there is office hours also tomorrow afternoon, so if somebody wants to ask questions. You wrote with him, it's really sad that I can't see you because I always see the mask, okay, so it's really, so please, can you show me your, okay, just, okay, thanks, just put your mask. Yes, so you wrote me about the hour, so about the precise hour, when you can come. It's from 2:30, but at 2:30 there is already another student coming there. I mean, maybe you are the same student. Let's come at 2:30, okay? So if you are two, there is enough space in my office. You listen to each other's questions. So what is? No problem. Okay, see you tomorrow at 2:30. Okay. Okay, bye. Okay, so bye. See you tomorrow at 9. So what's your name? The examination. Because I remember that I explained everything at the beginning of the course, but maybe it's better to repeat it. Okay, so there is a midterm examination for those students who want to exploit the midterm examination. Then there is, in January 18, I guess, there is the possibility to take both the full examination and the second midterm, okay? But there are, in that date, there are two separate lists, two separate exams and two separate hours also, okay? In the same day. So you have to select in advance which one you want to take. You may, for instance, suppose that your grade in the midterm examination is 23 or you don't like it, okay? You want to reject this grade and take the full examination in January. You don't need to send me an email in which you reject the grade, because we don't reject grades of midterm examinations. The only grades that can be rejected are the final grades for an examination, okay? So just come to the full exam. I see that you participate in the full exam, and this means that your midterm exam is automatically cancelled, but then it cannot be recovered. So, I mean, if you fail the full examination, you can't, in the second winter session in February, ask me to recover the midterm and take the second midterm. Because there is also the possibility for the second midterm in February, only for students who didn't take the second midterm in January or the full exam in January, okay? Students who took the first midterm in November can directly take the second midterm in February. But in February, they can also take the full exam.
Okay, because on the exam, it's written.
Yeah, and this, I can explain to you the reason, but I'm not sure. Because it's, I mean, in principle, the possibility to split the exam in two parts is only for the first winter exam date. So there is no possibility to do that formally, to do that for two different exams, okay? The second date should be only a full exam. But I see that many students like to have the flexibility to decide whether to take the second midterm in January or February. So I allow this possibility to you, okay? But of course, you cannot take both. You have to decide whether to take the second midterm in January or in February. And also, officially in AMA Esami, there is no separation between the two different exams, okay? You will be all in the same room. You will see appearing both the second midterm and the full exam, and at the moment you will decide which one to take, and you will upload correspondingly your exam.
Sorry, the last question. If we take the second midterm in January and then we decide to reject the grade,
you can
the entire one in February?
You can take the full exam in February, which is about 2 weeks later.
Yes.
Of course, there is no salto d'appello. There is no, I mean, you can take every exam date. You can use every exam, also because they are only three. Yes. They are only three. So I am also trying to multiply, to expand them with this possibility of doubling basically the possibilities both in January and in February. I'm also trying to expand a little bit the range of exam dates, in a sense, the range of possibilities. So I think it's useful for you and for me as well. Because in this way, there are only few students in general that have to take the exam in September or the next year, okay? So I see that more or less 80% of the students succeed in finishing by February.
Okay. Thank you very much.
Okay, you're welcome. Arrivederci.